Now, CL8 in and of itself is an algebra worth paying attention to for a number of reasons. Number one, it has roughly the right number of degrees of freedom for the Standard Model's off-shell or unconstrained states. Number two, in the world of real Clifford algebras, CL8 is essentially unavoidable. Well, what do I mean by unavoidable? Well, let's say we were to consider the space of all real Clifford algebras of the form CLST. Well, here the S and T can be any integers greater than or equal to 0. So there's an infinite number of these Clifford algebras. Then Bott periodicity tells us that if you were to choose one of these CLSTs at random out of this infinite set, then with overwhelming probability, that Clifford algebra will be of this form. That is CLS0T0 cross CL8 cross CL8 cross CL8 and so on, where the S0 and T0 are each between 0 and 7 inclusive. So in other words, we've got this little n piece, CLS0T0, followed by a long string of CL8 cross CL8 cross CL8 cross CL8. So this is going to be overwhelmingly dominated by factors of CL8. And it's in this sense that I mean to say that CL8 is unavoidable. So this touches on a point that I would like to make about which mathematical structure we choose when we're building physical theories. That is, when a theorist is building a physical model, they could choose the prince of mathematical structures. That is, we could look for the mathematical structure that is somehow the most distinguished or the most special. Or alternatively, we could instead opt for a mathematical structure that is somehow the most common. Now, CL8 is an example of a mathematical structure that is the most common, at least within the space of real Clifford algebras. So we could say that CL8 is special because it is not special. Now, a third reason why I find CL08 interesting is because it looks, loosely speaking, like it might give us a natural incarnation of a Fock space. So let's say we can indeed describe a state in the Standard Model as an element of CL08. And this is what we're going to argue shortly. Then this would count as a one-particle state. Okay, so now let's say again that we were to take some Clifford algebra, CLST, at random. Then an element of this space might be viewed as some sort of a multi-particle state. And here the number of particles in this multi-particle state would correspond to the number of factors of CL8 that the Clifford algebra has. Then finally, taking superpositions over different sized Clifford algebras could give us something along the lines of a Bott periodic Fock space. So here we start with a 0-particle state, and then we add in a 1-particle state, a 2-particle state, and so on. We might decide to interpret the CLS0T0 piece as a rudimentary algebraic beginnings of a spacetime with S0 the number of spatial dimensions and T0 the number of time dimensions. Finally, we might even decide to include the totality of all real Clifford algebras by summing over all possible S and T indices. This can be thought of as a sum over a finite number of spacetimes. I should mention that it may be useful at some point to also consider graded tensor products, in that these might help us tease out fermionic and bosonic behavior. Now, to the best of my knowledge, this idea of a Bott periodic Fock space was first proposed here in 2021.